Welcome to MEERTALK. Hello, everybody. My name is Kaeza Fern, and I'm the Director of Communications at MEER. We are really happy to gather here together again for MEERTALK today. And I would love to begin by inviting everybody to turn your attention inward just for a moment and to feel your breath. And maybe say hello to the community of cells that makes up you. And let's remind ourselves of the wonder of this incredible system that is in relationship both to itself as a community and also to the billions of systems that are part of our beautiful planet Earth. Today, we will be hearing from our guest speaker, Dan Cziczo, a climate researcher and entrepreneur. Then we will have a question and discussion period with three of our student researchers, Sky Lam, Anthony Han, and Albert Chang. And in the final section, we will hear from you what your questions are. So let's get started, and I'm going to tell you a little bit about Dan Cziczo. Dan Cziczo is an atmospheric scientist interested in the interrelationship of particulate matter and cloud formation. His research utilizes laboratory and field studies to elucidate how small particles interact with water vapor to form droplets and ice crystals, which are important players in Earth's climate system. If anyone has any questions come up while Dan is presenting, please send them to MEER's Director of Strategy, Peter Dines, in the chat. And Peter should be showing as co-host. Okay, Dan, so glad to have you today. Thanks for joining.
Well, thank you so much for having me. I wanted to say thank you to you, TA, and Peter for having me this Sunday afternoon, and it's a real pleasure to have a chance to talk with everybody here. If anybody is unclear of anything, Kaisa, I don't know if you or Peter would like to go ahead and break in the talk. If there's anything that is unclear, I'm happy to do that. Otherwise, I'm going to take about 20 to 25 minutes to just go through, what we wanted to talk about today, which is the known unknowns in stratospheric aerosol injection proposals. And so what I wanted to start by doing, let me just make sure that I can advance my slides. I wanted to start by doing a little bit more of an introduction. So thank you for that introduction on the research that we do. This is actually something that we've started doing in our seminars here at the university, which is to ask speakers to say a little something about themselves and how they got to the point in their career that they are. So I actually started out life as an aerospace engineer. I guess I shouldn't say life, but my professional career. And I was working on this spacecraft. This is Galileo. And I was working as an engineer. And one of the things that we were doing was interrogating the atmosphere of Jupiter. And this led me to become very interested in planetary atmospheres. And the one that is closest to home, of course, is Earth's atmosphere. And I started to do some graduate work, not in a spacecraft sense, but actually in a laboratory sense. And so this is an old photo in the days that we didn't even have digital cameras or anything like that. And so this is something that I had to redigitize to put on here. But this is our laboratory at the University of Chicago in the late 1990s. And for those of us that are old enough to remember, we weren't really even talking that much about climate change at this point. But my advisor had a great deal of foresight and was starting to think about the interrelationship of particulate matter in our atmosphere, greenhouse gases, how those particles could form clouds, something we'll talk about more. And we were starting to do some of the early research on this topic. And this is really going to be sort of a theme throughout the talk today. After I finished my graduate work, I had a chance, this is a much younger version of me on the left, working on some NASA research aircraft, actually building instruments to look at particles and clouds in our upper atmosphere and try to understand them. And this is a much more recent picture actually from this summer where we're doing some research right now, just finishing up in the next few weeks, continuing to look at the changes that are induced by human as well as by natural causes to our atmosphere. And so this is Justin Jacquot, who's a fantastic postdoc in the group, and the photo was actually taken by another fantastic postdoc that we have, Xiaoli Shen. And so the reason that I wanted to do this quick introduction to get started is to give you all some sense of the fact that I'm very much an experimentalist at heart. I work on particles, I work on clouds. I do this in the laboratory. My group and I do field studies as well. I'm not a modeler. I'm going to talk a little bit about modeling results today, but I'm not personally a modeler other than to use models to some extent. And I think it's important that we all sort of mention these things because we come with our own strengths in these areas. I hope I've kind of given you an idea of what I've done before, but also our biases. And so I'm very much biased in the sense of, what does our atmosphere look like? What can we measure? What can't we measure? What's known? What's not known? And I hope that's reflected in sort of the title of the talk and what I bring to you today. So where do we want to get started? Kaisa was very kind to give me some insight that some of the folks here are very much experts in this area, and I've had a chance to look at some of the talks that MEERTALKs have done in the past. And so I also understand that there's some folks here that might need a bit of a refresher, and I'm glad that I've had a chance to work with some adult STEM organizations and give talks very much like this. So where I thought we'd get started is to talk about Earth's climate and how we might be thinking about altering it. And so this is a slide that is from the 6th assessment report of the Intergovernmental Panel on Climate Change, the so-called IPCC, the one that just came out this year. And what's shown here is the observed warming in our planet. That's shown on the left-hand side, how much our planet has warmed, something over a degree, approaching 1.5 degrees C. And then it breaks it down into what we as scientists believe the major causes are. And things that are red here that are positive, that fall above 0 on the y-axis, are things that are warming our climate. And so you can see that the big one here is well-mixed greenhouse gases. And so this is well known, I think, to most of the folks here today. Carbon dioxide, methane, nitrous oxide, and others are warming our planet. What's maybe not as well known is that there's other human drivers. There's other things that we're doing to the Earth system that are actually cooling. They're offsetting some amount of that global warming. They're not able to erase it, but they are reducing it to some extent. And if we think about what the warming agents are versus what the cooling agents are, the warming agents are these greenhouse gases that we've all heard so much about. The cooling agents tend to be the particulate matter that we as humans are putting into our atmosphere. Predominantly organic carbon, small organic aerosols, as well as sulfur dioxide, which finds its way to making sulfuric acid and other sulfate particles. There's other things that add to these particles. You can see ammonia here. There's some lesser ones that are also known. But these particles reflect a great deal of sunlight. They actually also form the seeds for clouds. So clouds form on existing aerosol particles. So as we increase the aerosol loading of our planet, we actually change clouds. We increase the clouds in our atmosphere, which has other secondary effects. And so what I want to get across with this slide is that when we start thinking about changes that we could induce on our planet, changes that we have induced, we get warming from greenhouse gases, we get cooling from things like particles and clouds. And so when people have started to think about geoengineering topics, what they've often thought about is, can we remove the greenhouse gases? This is normally called carbon sequestration. We also have some ideas for things that could be done to change particles and clouds. And these are the things that we're going to be talking more about today, especially in the sense of things that could be done in the next layer of our atmosphere up, the stratosphere. And so I'm going to go ahead and let this clip play. We, in starting this, realized that I can't hear it, but hopefully you all can. And if there's any problems, go ahead and just let me know.
A net cool climate science. Take a cloud, and we're going to do it in this little jar right here. So to get started, this is going to mimic a cloud that's going to form over a body of water like an ocean, so that you can see the bottom of this has a bit of water in it. So you could pretend that we're going to make a cloud, say, over the ocean off of the coast of Boston or something like that. Normally, clouds form by convective activity. The surface of the Earth heats up, the air is somewhat warmer, and then it moves upward in the atmosphere. And as it does that, the relative humidity increases, the temperature decreases, you hit 100% relative humidity, and your cloud forms. Unfortunately, I am not tall enough to lift this quickly enough to get a cloud to form in it. So instead, what we're going to use is a pump to drop the pressure in this and mimic that cloud moving up, or that air moving up and forming the cloud in the atmosphere. And you can tell the pump is on because when I put my finger over this little filter right here, you'll hear a slight sucking noise. And that's the pressure in the jar dropping, which is going to be akin to this moving up in the atmosphere. And I can hold my finger over this for quite a bit of time, and you won't see anything happen in the jar inside. There's no cloud forming. And the reason that there's no cloud forming is that this little piece right here is actually a filter. So it's taking all of the particles out of the atmosphere before they make it into the jar. So this jar right now is only air. There's no particulate matter in it whatsoever. As the pressure drops, the relative humidity is going up quite a ways. It probably is reaching 110, 120% relative humidity, a humidity that you would never hear on the nightly news, and yet there's no cloud that's forming. So what we have to do is introduce particles into this jar to get the cloud to form. We're going to do this with a common household match, and you can imagine that this is going to mimic a process like burning down a forest, wildfires, that's going to add particles to the atmosphere. So we first light the match, and then to get the particles to form, you'll see the smoke come off in just a moment. So here's the smoke. We let it into the jar. The jar now has particles inside of it, and when we do that, the cloud can form on those particles that we've put into it. We'll let the relative humidity go down, and the cloud goes away. There's still some particles in there, though, and so another cloud will form on the particles that are left over. We can let some more air into the jar, and yet more particles will form on a cloud. You'll notice that the cloud becomes thinner and thinner each time because we're removing particles every time I open this up and they're pumped away. So obviously this is not a high-tech cloud chamber. This is not something that we can use to produce laboratory quality data.
Okay, so hopefully that came across okay and you guys had a good view of the video. The real point that I wanted to make with that video was to really hammer home this idea that particles in our atmosphere are absolutely critical for the formation of clouds. So as we think about any changes to our atmosphere, intentional or unintentional, that change particles, we're going to have an impact on clouds. Those two things are going to impact climate. They're going to have impacts on the precipitation of the atmosphere. They're going to be able to do things like induce droughts in areas or induce flooding in areas anytime we change those particles. We've probably already done that unintentionally with the changes that we've made to our atmosphere since pre-industrial times, but any future changes that we think of are going to have the same potential impact. The other thing that I'd like to get across is that in that video, we did a very, very rudimentary study where we've sort of put in these biomass burning particles from a match. So all the particles were of the same kind, but if we start changing or doing different things, if we have different chemical composition of those particles, they're going to have different cloud formation properties. So we're going to end up not really understanding fully what the impact is on the atmosphere until we do the full experiments that we need to in the lab behind those things. So that's the real point that we wanted to get at. So that's the sort of overview of climate and changes that might be made to the climate system. And so now I want to dive into what it is that I'm here to talk about today, which is this idea of changes that we as humans might propose to our stratosphere to offset global warming to some extent. And the reason that I started doing this was actually because of a small paper we wrote about 1.5 years ago. And because of that paper, which I'll talk about today, I got an invite from Karen Rosenloff, who's a scientist at the National Oceanic and Atmospheric Administration, to give a talk in what they called their Geoengineering Modeling Consortium. And when she made the invite, this is several months ago now, she asked if I would be able to discuss designer aerosols for stratospheric injection, things that we might intentionally put into our stratosphere. Again, the next layer of our atmosphere up. We all live in the troposphere, so this is the next layer up. And what we might need to know to make sure that we can predict the outcome of any changes that we were to introduce. And Karen specifically mentioned 2 papers that she wanted me to address. These are by David Keith and John Dykema. So the papers are shown here. These are David and Frank on these papers are professors at Harvard. John is a research scientist there. I actually had a chance to just email with Frank today. I don't think he's here. He mentioned that he was traveling, but if any of the folks are here and can jump in afterwards, I'd very much welcome that. I've had a chance to talk to them about this, but I'd always seek out their further advice. So one of the things that Karen asked was, can I sort of address what these papers are proposing, what's known about that, and then what's also not known about that? Okay, so this starts out with this concept of what do we mean by a designer aerosol? And the idea here is that, maybe we don't just increase the amount of particulate matter in our atmosphere, in the stratosphere specifically, but we think about what negative effects particles can have in the atmosphere. And the one that has been brought up greatly is if you just increase particulate mass in the stratosphere, it has a lot of known negative effects, such as increased particle mass will lead to a decrease in stratospheric ozone. And for those of us old enough to remember the ozone hole days or the initial days of the ozone hole, this came with increases in things like skin cancer, other adverse effects that we are going to try to avoid. The other idea behind designer aerosols is maybe you could actually engineer them in such a way that they would have a positive impact. And so the authors of these papers suggested that if certain materials, predominantly calcium carbonate, were put there, that they might not be as reactive, they might not cause ozone loss, but they also might be able to react with certain chemicals in the stratosphere, actually act as a sink and pull them out. Predominantly acids that are in the stratosphere that might lead themselves to ozone loss. So the idea was, could you put something there that's not reactive to ozone, but might actually cause a quote unquote healing effect? So the question is, well, how might this work? And again, I'm sort of distilling what was in these papers. This is the one by John Dykema. And what he proposed doing was putting enough material into the stratosphere on the order of about 5 teragrams of material, and I'll talk more about what that means in just a moment, of material, enough material that it would scatter solar radiation back to space, thereby cooling the planet equivalent to how much warming has gone on because of greenhouse gases, essentially canceling that bar out that we saw before in one of those early slides. This amount of calcite would also have the impact of pulling some of these acids out of the stratosphere, potentially helping in ozone recovery. So this is the general idea here. They sort of focused on calcite as being similar enough, or having scattering properties similar enough to the existing stratospheric aerosol, that it was fairly well known what these materials would do. And I just wanted to point out that, how much is this sort of idea of 5 teragrams of material moving into the stratosphere? So I have a hard time thinking of what a teragram is. A teragram is about 10 aircraft carriers. So we're talking about putting about 50 teragrams of material, 5 teragrams of material, about 50 aircraft carriers of material into the stratosphere every year. Those particles fall out on about an annual basis. That's about their lifetime in the stratosphere. And so you would need to replace that material. In a more terrestrial sense, a major dust storm usually has several teragrams of dust. And so this is a dust storm that came off of the African continent a couple of years ago. And this is estimated to have about 5 teragrams of material. So that's the volume of material, the mass material that you would need to put into the stratosphere. So I promised Kaeza that I wasn't going to show too much chemistry, but I think that this is important because of the theory of what's going on. So the concept here is that this calcium carbonate, CaCO3, would react with these stratospheric acids. So this is sulfuric acid on top. This is nitric acid and hydrochloric acid. It's going to react with those materials. It's going to bind them into the particle, and then those particles are going to fall out of the atmosphere. This is the theory. And so when Karen asked me to give this talk at NOAA, one of the things that she asked me to discuss was, what do models need to better represent stratospheric aerosol processes so that we might get this chemistry right? We might be able to predict it if we were ever to do these types of things. So one of the things that models currently have is an understanding of the stratospheric aerosol, but they're very simplistic. They sort of think of what's in the stratosphere as just sulfuric acid and water, which that's what it's majorly composed of. But we'll talk more about this assumption in a few moments. The other assumption that they make is that these sulfuric acid water aerosols that are natural are chemically reactive. This proposal assumes that you inject calcium carbonate, which is non-reactive itself, and that it only creates anhydrous, essentially dry products, calcium sulfate, calcium nitrate, calcium chloride, which then themselves sort of bind these acids up and then fall out of the stratosphere, and nothing more takes place. So this word anhydrous or dry has a lot of assumptions behind it. And so one of the things that we started doing in our group was to sort of look into the historic literature. And so there's good news and bad news here. The good news is that you can go back and mine literature and find really interesting answers to questions that you might pose without actually having to do experiments. And so the good news is we found some interesting literature. The bad news is that it was very difficult to find. It wasn't in the atmospheric science literature. So we had to dig rather deeply. It turned out that a lot of this was from industrial technologies. So this was a very obscure paper on modeling calcium carbonate neutralization in the presence of armoring. It was something that was written for some industrial processes, and it was written in Italy. It was translated into English, and we found it in an applied mathematical modeling journal. So not something that we as atmospheric scientists would normally read. We were also able to find some of the chemistry involved in this in industrial journals that dealt with gypsum. And so this was quite interesting because this was something done for applications related to manufacturing of drywall, but you can see a lot of the chemistry that we just spoke about that's theorized to go on in the atmosphere actually is going on in this literature. Another place that we found it was in atmospheric science, but not terrestrial atmospheric science. These were some studies that were done for Martian atmospheric science. And the authors noted that this might be applicable cold temperature wise to Antarctica on Earth. It's equally applicable to changes that we might make in our stratosphere, which is very low pressure and very low temperature. And so we were able to find a lot of the answers to the questions that were posed in these two papers in historical journal articles, but again, not things that we would normally have looked at. And so one of the things that we found out was that, really these two assumptions, that the background aerosol and the proposed material for injection didn't act at all the way that the authors thought that they would. Calcium sulfate formation, this armoring process, which is known again from industrial applications, forms what the authors noted was an armor to the surface, so that as the first sulfate molecules made their way to the surface, it created sort of an impenetrable barrier. So this idea that you could sort of put calcium carbonate there and it would react with these acids and remove them from the atmosphere is not the case because there's this barrier created. So a lot of that assumption was simply not true. A secondary assumption was that these materials would form anhydrous or dry materials. And that was also from the literature shown to not be true, that in fact, we create a great deal of hydrates. So sort of crystalline structures that incorporate water in them. And something that we've known for quite a while, ever since the ozone hole days, is that hydrates can be very chemically reactive. And so the first answer that we sort of brought to Karen in this geoengineering modeling consortium was that we often need to go further than a proposal, but actually look at the literature and perhaps do some experiments in order to really correctly model the evolution of these particles. These sort of basic assumptions were simply not correct. The second thing that we were able to do in our lab, and something that I mentioned in that earlier video clip, was that was a very rudimentary cloud chamber that you saw, that sort of bell jar with particles from a match. But we were able to do some experiments with some of our higher tech cloud chambers that we had in our laboratory. And with these, we were able to see how the particles that were proposed to be put into the stratosphere might participate in cloud formation. So we looked at calcium carbonate. Those are the red figures here, or the red data points here. And we were able to look at some of the other materials that calcium carbonate might react to form, including some of these hydrates, which can be highly reactive. And so this is a bit of a busy plot, so I'll try to explain it. Ice saturation ratio on the y-axis here is another way of saying relative humidity. So 1.1 ice saturation ratio is actually a relative humidity of 110%. And so what you can see is that things like calcium nitrate, CaNO3 taken twice, exist on this sort of dotted line up by about 1.5, 150% relative humidity. And so at these very cold temperatures, that might be where we would expect clouds to form. The materials that we see here at about 1.3, 130% relative humidity are materials that would be very good at forming new clouds in our atmosphere. And so I really want to hammer this point home, because what this proposal would lead to is not simply putting material there that would scatter radiation into space. It would actually make particles that would be good at forming new clouds in our atmosphere. And again, to sort of repeat what I said earlier, these new clouds would have the potential to change the precipitation in our atmosphere. They themselves would change the radiative balance. They would change the climate of our planet in a way that wasn't predicted by a simple idea of just putting particles into our stratosphere. So to try to start, sort of finishing up this talk, I'd like to sort of wrap up this idea and say that, very often these simple proposals, this idea of putting 5 teragrams of material into our stratosphere to cancel out about 2 watts per meter squared of warming, have a lot of assumptions in them that we have to really question. And so the first thing that we were able to do was, by looking at global climate models, show that in this paper, the idea that minus 2 watts per meter squared by this amount of material would be the result are actually not exactly true. There's other models, model to model differences, that would say that it's somewhat less, maybe on the order of about 25% less, 1.5 watts per meter squared. Another thing that was shown in these models is that you can't just consider what happens in the upper atmosphere where you might scatter sunlight. You have to also think, are you scattering sunlight above an existing cloud? This is a concept called cloud shielding. And if you would have scattered that sunlight away anyways, you don't really get to count it twice. You only get to count it once. And so now you've dropped from an effective 2 watts per meter squared to about 1.5, and then further down to about 1 by considering lower lying clouds. And then if you think about the new clouds that you could form, this falls yet further to something under 50% of the impact that was suggested in this proposal. So even if everything else was right, even if all of the chemistry was right, which I think I've shown it wasn't, that 5 teragrams of material that you're putting up there was probably at least a factor of 2 or more low. And so we would have to reconsider, is it something that you would consider doing if you had to sort of double the impact or double the amount of material that you'd have to put up every year? I do want to slow down and explain this with an image of our atmosphere. So again, troposphere is the part that we live in at the bottom. Stratosphere is the next layer up, and that has the ozone layer in it. And so the proposals that we're talking about today sort of suggest sunlight coming through our atmosphere, and then perhaps we put some extra particles into this stratosphere that would scatter those back to space. But if we think about these proposals, we have to think about the likelihood of those particles scattering above a pre-existing cloud. If we don't do that, we're not doing our counting appropriately. And then on top of that, we have to think about those particles not just sort of disappearing when they leave the stratosphere, but instead, what might they do as they fall out of the stratosphere? And again, they would fall out on about an annual basis. And so I think what I've shown is that a lot of those particles are going to create lower level clouds, which we term cirrus clouds. And those clouds actually can trap some of Earth's heat being put off. They can act essentially like a greenhouse gas. And so now we offset further anything that we do in our stratosphere. So the second answer that we sort of gave to Karen was that to do this properly, you need to really correctly model the existing and modified clouds. So not just get clouds right in our current climate, but also think about the impact that these particles, these changes are going to have on sort of a future atmosphere and modified clouds. So as I mentioned, I'm just going to wrap up. And as we were preparing for this talk, I was asked a question about what we were doing right now. And sorry, if there's an existing laser pointer here, so hopefully that's not too distracting. It's I'm watching it move around as well. But so what we're working on right now is actually some measurements in our upper atmosphere. We're working on the plane on the left here. This is NASA's ER-2 aircraft, and this goes up to about 70,000 feet. So this is almost 20 kilometers in altitude, so well into the stratosphere. We're not looking at geoengineering per se this year, but what we're trying to do is better understand the complexity of our atmosphere. And so one of the things that I mentioned earlier was that a lot of these models right now very simplistically assume that all of the particles in sort of an unperturbed stratosphere are sulfuric acid and water. I should mention that the plane on the right is another NASA research aircraft. This is the B-57, and some of our colleagues at NOAA are actually flying on this. It's got a somewhat lower altitude, but also makes it well into the stratosphere. And so one of our major objectives this year is to look at intense thunderstorms and how they might basically punch material into the stratosphere. So again, I'm showing a scientific plot here. Potential temperature on the y-axis is a sort of a proxy for altitude. The stratosphere starts at a potential temperature of about 380 Kelvin. And so what you see with this solid line here is biomass burning particles in the stratosphere. And so I'm trying to bring things back to those particles I showed you forming clouds earlier in that very simple bell jar experiment. And so one of the things that we've seen is that intense thunderstorms can push material from forest fires into our stratosphere. These are very common materials that are found in the stratosphere. They're obviously not sulfates. They're residual particles from biomass burning, wood burning, grass burning, that type of thing. And so this is something that isn't properly portrayed in any climate model right now, much less the ones that are considering geoengineering. And so again, the point to hammer home here is that if we don't understand our atmosphere right now, we're really not able to think of proposals that have any real certainty on working out the way that we want them to in the future. So I'm going to just put up a couple of conclusions here from this quick talk, and again, say thank you to the organizers for having me today. I hope that I've convinced you that stratospheric particles in chemistry are much more complicated than is typically acknowledged. I hope I've also explained to you that geoengineering proposals often don't capture the complexity of our stratosphere with the plans that they make. This might be from a lack of understanding of the current literature, but also can be a result of just not understanding our atmosphere as well as we possibly could. And then finally, understanding the current state of the upper troposphere and stratosphere is critical for anything that we do, just climate change on its own, as well as climate change, as well as these geoengineering proposals. So before I turn it over to questions, I just wanted to close by saying that I think that in some sense, we've almost become divided into a couple camps here, sort of pro geoengineering or anti-geoengineering. And I don't really think that's the right way to look at it. I myself am very much pro carbon sequestration. I think that that's a very well-known technology. It's a very well-known impact that it would have on our atmosphere if we started to remove CO2. I am very much against stratospheric modification because of all the uncertainties that go with them. The possible changes in our ozone layer, thinning of our ozone layer, increases of skin cancer, changes in precipitation inducing droughts or creating flooding, as well as unabated ocean acidification, which if you only change the stratospheric aerosol layer, you're not doing anything about ocean acidification. So for me, these are red lines that I don't want to cross. The folks that are listening today might differ in those. I'm very happy to talk about those. But what I would say is just, as long as you're well informed in making your decisions, that's really what the critical thing is. And so with that, I'd like to just say thank you to Kaisa, Ye, and Peter again for having me today. I'm very happy now to turn it over to the students and then take any questions that the group might have. So thank you again.
Great. Thank you so much, Dan. That it is incredibly complex, but we've seen more about that complexity. And I am just really glad you are studying about this while people are considering this as a method. So what we're going to do now is bring on 3 of our student researchers, Sky Lam, Anthony Han, and Albert Chang. And they have some questions that they'd like to ask you. Sky Lam is a high-achieving scholar who has a strong passion for saving the environment, whether it be conducting notable research in climate change or leading youth activism events around his community. At Harvard University, Sky plans to pursue a degree in a STEM-related field and continue to utilize his experience in environmental sciences to make the world a better place. Anthony Han currently studies chemical engineering and data science at the University of California, Berkeley. Passionate about mitigating climate change and positively impacting the world, He is currently analyzing nitric oxide emission trends from industrial fossil fuel combustion to generate nitrogen-based products efficiently. And then Albert Chang, is analyzing nitrogen oxide emissions trends from industrial fossil fuel combustion on the nitrogen oxide valorization team, and is also designing an exterior radiant barrier roof. He studies mechanical engineering at the University of California, San Diego, and is interested in sustainable energy distribution to mitigate the impacts of climate change.
All right, thank you so much for taking the time to speak with us today. To start off our discussion, I want to ask the following question. What governing body should be overseeing the policy decision-making process informed by our current research of stratospheric albedo modification? And is there such an organization already in place?
Ooh, wow. You're not starting out with the easy questions today. First off, thank you again for having me, and really a pleasure to talk to you guys. Yeah, I think if I can maybe just take one step back from your question, I think it's really, really important because I fear that as scientists, we've almost jumped into this policy realm that we probably shouldn't be. So, we as scientists can talk to people about what we know about the atmosphere, about potential sort of theoretical approaches to geoengineering. We can talk maybe a little bit about what effect that they might have, or like today's talk, what are the unknown parts of those? What are the slippery slopes? What are the things that might happen? But unfortunately, I think as scientists, we've been asked to take off the scientist hat and sort of put on a policymaker hat. Of course, the Intergovernmental Panel on Climate Change that we mentioned earlier is sort of the body that produces these reports every 4 to 6 years, depending. And those are really meant to go to the world's governments. And so the idea is, and of course, we have some of these domestically as well, like the climate report that came out, I guess it was 2 years ago now, just from the US government. Those are meant to just be reports. We're supposed to be giving information to governing bodies, but not ourselves trying to influence policy. So it's a great question. United Nations, bodies that are associated with the United Nations, G7, groups like that, those are the ones that should really be putting together, sort of policy-making bodies and having these discussions. And we as scientists, I think, what we should be doing is giving them the information that they ask for, but not necessarily being advocates one way or another. I tried to say at the end where my personal red lines were, but I'm not sure that we as scientists should be the ones influencing those decisions. So I'm sorry, that's a bit of a roundabout way of answering your question, but I hope it's helpful.
Yeah, thank you for your insights. But for a more science-based question, how does the radiative cooling and warming effects change for clouds at different altitudes, for different seasons, and for different locations?
Oh, yeah, great question as well. Okay, so let's talk about this very generally. Again, this is something that I've got a great passion for, and I've been doing it for a couple of decades. The way that we tend to think about it is that lower lying clouds in the middle and lower stratosphere, in the middle and lower troposphere, tend to be cooling agents. They tend to reflect radiation back into space. As anybody that goes outside on a cloudy day knows, it's not going to be as hot as sitting in the direct sunlight. What's less well known is that the higher altitude clouds, these cirrus clouds that I mentioned at the end, and so these are the thin sort of wispy clouds that you can see when there aren't these lower lying clouds. Those exist very high in the troposphere, almost to the stratosphere. Those net tend to absorb more terrestrial radiation heat that's trying to escape the planet, and they can re-radiate that back downwards. They can act like a blanket. So they act more like a greenhouse gas. So the very general answer is that lower lying clouds tend to cool. They tend to reflect sunlight. Higher altitude clouds tend to be the ones that trap terrestrial radiation and can have an actual warming effect. So the altitude seems to be the critical thing. There's some other impacts that can be there as well, but that's maybe the high level answer to your question.
Yeah, Anthony, did you want to go ahead?
Yeah. All right. So my questions are more about like the process and chemistry of getting those nanoparticles to the stratosphere. So obviously when we think about this situation of like dropping nanoparticles into the stratosphere, right, is that one problem is that these planes that are used to drop those nanoparticles also produce nitrous oxides, carbon dioxide, and other byproducts. And we also mentioned like the chemistry part where there's also like some side reactions when you kind of just emit carbon dioxide after kind of reacting with the acids, right? So I do suspect that the quantities of these reactions are pretty small, but does the potency of the CO2 greenhouse effect depend on emission altitude?
Yeah, Anthony, you brought up a number of really important points here, and I would actually refer to you folks. I mentioned Karen Rosenloff at NOAA quite prominently. Hopefully she's a potential speaker for a future MEERTALK and can talk about these more intelligently than I can. So you're absolutely right. One of the reasons that I mentioned that the amount of material proposed to be injected is probably low, probably by a factor more than 2 is important, because that means that whatever energy you're expending to get that material there probably has to be doubled or more. And so if you're actually using aircraft to do that, then you're going to be emitting twice as much CO2 from those aircraft. Any other chemicals that are produced are probably going up by more than a factor of 2. And so most of the estimates are probably an underestimate of the adverse impact and an overestimate clearly of what would be derived from it. There are some interesting technologies that I've seen that have been proposed, putting up massive balloons that you would pump the material up there directly and you would maybe not have the emissions. I think those are kind of in the early stages of thinking right now. And I think that some of my colleagues, Dan Murphy at NOAA in particular, has talked about that, this would lead to a stratosphere, and this might get more to the heart of your question. I think this would lead to a stratosphere that's unlike anything that we really currently understand. So you're mentioning some of the nitrogen compounds, you're mentioning, some of the greenhouse gases, and those materials going into this Brave New World stratosphere is something that we really just don't understand. Your specific question about the emission altitude of the CO2 is a very good one. In general, CO2 at a lower altitude is going to have a higher impact because it's closer to the surface. It's going to act more efficiently as a blanket. If you put CO2 in space, it doesn't have that impact. So that's a very rough understanding of it. But certainly anywhere that you put it in the column of the atmosphere, anywhere in the troposphere, which is well mixed, it is still going to have a major impact. Essentially anything that is emitted in the troposphere, for all intents and purposes, if it's at ground level or just below the tropopause, those are really the first order the same. Stratosphere, it starts to get somewhat different. And of course, we are talking about having to emit these in the stratosphere. So I hope that answers the question.
Yeah. Do you think like the CO2 that's being produced whenever we move those calcite nanoparticles to the atmosphere, do you think that CO2 will have any long-term effect on global warming, or will it just be kind of mitigated?
Oh, I mean, boy, that's an even deeper question. So any CO2 that we put into the atmosphere for whatever reason, whether it be as part of a geoengineering idea or just from current existing fossil fuel burning, is going to have the same impact. And those things will be around for hundreds of years, if not millennia. So I shouldn't smile at that. I mean, that's just unfortunately the world that we live in. But those molecules are all going to have that long-term impact. We have to be very specific, though, that when we talk about these stratospheric proposals, these are things that are, at least people have been talking about as a stopgap, and so we're not really making a permanent solution. If we put a particle into the stratosphere and we stop doing it a year from now, it's gone, and we realize all of that global warming, and that CO2 molecule that we used or made to put that particle there, that's going to be there for, again, centuries and millennia, really. So again, this is why I'm a proponent of carbon sequestration, which is removing sort of the offending chemical species, as opposed to somehow trying to mask the effect, and I think, as you're pointing out, actually exacerbate the problem.
Yeah, so that was kind of what I was expecting for an answer as well. And I guess something that also relates to this is like, do you think that they would kind of amplify stratospheric clouds? Like, could they contribute to like nucleating ice particles, or not really?
No, it's a great point. So we should take one step back. Most of the clouds that we were talking about are tropospheric clouds, and just for the audience here, the vast majority of the clouds in our atmosphere are are tropospheric. Cirrus clouds being the highest ones that we were talking about earlier. There are polar stratospheric clouds, and these are well known from the ozone hole days. As the name implies, they're found predominantly in polar regions, almost exclusively, really. And these are the sites on which the catalytic reactions that led to ozone loss occurred. So in answer to your question, if you put particles in the stratosphere, some of those particles will find their way to the polar regions. Those particles, if they are good at nucleating ice, will nucleate new clouds there. Depending on whatever the future chemistry of the stratosphere looks like, they absolutely can be the sites for future catalytic reactions that lead to loss. But it's not just the clouds they form. Any particulate matter in the stratosphere is known to promote ozone loss. So when we've seen powerful volcanic eruptions in the past, things like those of us old enough to remember Pinatubo in the 1990s, we saw ozone loss afterwards, and it wasn't because of stratospheric cloud formation. It was just because of an enhancement of particles in the stratosphere. And so I guess it's double jeopardy in a sense. You're putting particles there that can promote ozone loss, and you're putting particles there that can form clouds that can promote ozone loss. So does that answer the question?
Yeah, thank you so much.
Absolutely.
Sorry, I have one more question. I know this is a bit long. But what are the effects of those compounds that you create in the atmosphere, like calcium chloride, and what happens like when they precipitate from the atmosphere onto the Earth's surface? Because I think chlorine is not one of the best elements. So just putting that out there.
Yeah, that's actually for people that do air quality. So maybe another future MEERTALK. I guess we've already proposed 2 future MEERTALKs here. So you're absolutely right. What you're going to do is you know what goes up must come down. So if you're putting 5 or 10 teragrams a year of material into the stratosphere, and maybe you have some of these chemical reactions so that the mass that falls out is actually even greater than that, that has to go somewhere. So my group and I have been looking at cloud formation, precipitation changes, but that material will still fall out yet further, ultimately, as you point out, to the atmosphere, to the surface of the planet. And what that does at those points, I don't know that that's been well studied. I know that there's a few studies that say, well, atmospheric particulate loading is much greater than 5 or 10 teragrams, and so maybe it's sort of in the noise. But I don't know that that's been fully worked out. And so yeah, you may think about inviting somebody in that does sort of lower atmospheric air quality to talk about that.
Sounds good. Thank you so much for answering my questions. I'm going to pass it on to Albert, who has a couple more for you.
Thank you.
Thanks, Anthony. Hey, Dan. My first question is, what do you think are the key aspects of cloud formation research and milestones that must be achieved before it can even be admitted for discussion in, let's say, the general public or policy arena?
Oh, wow. Great question. Yeah, I think one of the reasons my group and I do cloud formation is, it's a scientifically interesting problem. And one of the reasons for that is that it's so poorly understood. In the 20 years that I've been doing this, we went from a world where we thought we knew all about nucleation of water and ice in the atmosphere. We thought we had worked out everything. And maybe 15 years ago, we realized that we didn't know anything. And so every day there's new mechanisms for ice nucleation in particular being proposed. There's people that used to think that the size of the particle was the determinant of if it formed a droplet. And, again, 15 years ago or so, the chemistry of that particle was realized to be a major player in the formation of the droplet. And so, this is a very selfish way of answering, and I appreciate the question. I think the nucleation part of it is something that we just simply don't know enough about. We don't know all of the formation mechanisms of ice. We don't know how the chemistry of these particles plays into nucleation of droplets even. And then, taking it a step further, as we as humans, industrial and agricultural other applications put particles into the atmosphere, we don't really know necessarily what all those particles do, what their ultimate fate is. My group and I looked at things like historic lead from leaded gas emissions a number of years ago, and found out that they were probably very good at forming clouds, and there might have been a lot of these clouds formed in the 1960s and 1970s. Before we really had enough satellites to be able to see what we were doing to our atmosphere. So I think that there's an abundance of things from the fundamental science of nucleation to the modeling. And one of the things that I tried to mention was that I think that the models are really only as good as the data that we as experimentalists give them. But they're also computationally limited. And so, until we're able to really track all these nuances of particles, and carry more complexity of the chemistry and the nucleation, the models will never be 100% accurate at clouds or precipitation. So I would say those are the two big things: enhances of computational ability of the sort of ability of the models, but also the underlying microphysics of what's going on. Yeah, great question.
Thank you. And this is more of a higher overview question. I know you mentioned that you're not too strong of a proponent of aerosol injection. And this is more sort of related to what we do here at MEER, which is also trying to find alternate solutions. So given the time constraints, how should we as scientists approach the research, funding, and implementation of aerosol injection or any other solar radiation management project to be a feasible solution for the climate crisis, given this danger that we're in at the moment?
Oh, wow. This was it's a loaded question like the first one. No, thank you. It's a great topic, and this is one that we can all discuss further. I do want to be very careful, much like the first question, that I almost have to take my scientist hat on and often put on my sort of citizen hat for a moment. The reason that I'm more of a proponent of things like carbon sequestration is that we have an understanding from sort of recent climate history as well as paleoclimate of what our planet looks like as we moved from pre-industrial times from sort of 280 parts per million carbon dioxide to the world we live in now, 400 or more parts per million carbon dioxide. And so if you start to remove the carbon dioxide, if that's your geoengineering proposal, you can sort of imagine that we sort of know what a world would look like moving backwards on that curve. There probably are some switches in there. There's probably step functions. So going backwards, not 100% analogy to moving forwards. I admit that, but at least we would have something that looked like that past climate. The reason that I am not a proponent of injecting material into the atmosphere is it leads to an atmosphere that we really have no understanding of. An atmosphere with 400 or more parts per million carbon dioxide and who knows what in the stratosphere, maybe different cloud coverage in the troposphere. That's just something that I don't think any model has been trained to do, and I don't really have any faith that we know what it would look like. I think that at MEER, from what I understand, ideas of reflecting energy back into space, whether that be by land surface changes, things like that, I think that that's more of a known quantity. The atmosphere is more understood. A change in surface albedo has been done intentionally or unintentionally. Deforestation is a change in surface albedo. Loss of ice cover is a change in surface albedo. I think those are things that we, as scientists, have some understanding of. So I think moving in those directions, of course, are things that would at the very least, be better understood. They wouldn't have the impact that I'm kind of warning of: changes in ozone layer, changes in precipitation, that type of thing. And then one other thing that we really need to talk about is that any change that masks just incoming sunlight doesn't actually do anything about ocean acidification. If you're still ramping up CO2, that is still a major, major problem, and one that you really don't get away from unless you start pulling CO2 down. So again, a reason that I'm a proponent for the pulling down.
Awesome. And I just have one follow-up question to the last part of your question. So you mentioned, unless we start cutting CO2 and greenhouse gas emissions and trying to sequester these greenhouse gases in the atmosphere. I think one also known thing is that the current smog and emissions also provide a sort of temperature relief and masking of sunlight, incoming sunlight. So can you think of any other detriments of this transition?
Yeah, that's actually a really good question. So just for the audience again, we have actually, especially in North America and Western Europe, done a pretty good job of sort of cleaning up particulate emissions. There is some evidence that particle loading was much higher, and we actually had some amount of global dimming in the 1970s, early 1980s. And so some of the rise in temperature might actually be because that cooling bar I showed in that early slide is actually smaller now. That's probably not true of Southeast Asia. There probably are enhancements of particles there. There's almost certainly enhancements of particles there. We can see them with satellite in other areas as well. So I want to be very clear about this. The health impact of particles is something that we really need to consider. So we should never consider leaving particles in the atmosphere because they have a cooling effect. They are too detrimental to human health. We can have some understanding that they're participating in the climate system, but for very different reasons, we really do need to clean them up. And that means continued vigilance in the places that have done a good job of cleaning them up, and increased sort of reduction of particles in developing areas where emissions are still on the rise. So I hope, does that answer the question? Is that what you're getting at?
Yeah, thank you so much for clarifying, and thank you for your responses.
Absolutely. Well, thank you for all the great questions.
Yes, thank you, Sky, Anthony, and Albert. And what we're going to do now is let our audience ask some questions. And so what you can do if you have questions, you can send them to Peter Dines in the chat. Peter is our director of strategy. And while we're waiting for those questions to come in, I wanted to announce that we are looking for some volunteers at the site, at an experiment site in New Hampshire. So if you live in New Hampshire in the United States, we have Plymouth State University and Concord Community College, our partners, setting up an experiment, and we need some people to help glue small glass plates to wooden block adapters that go between the mirrors and the posts. And there are a lot of there are 1,000 pieces, and it's really more than they can manage right now. So if you do happen to live in that area, you can reach out. I'll write the email into the chat in just a moment. So our first question for you, Dan, is from Reese. And the question is, how do we deal with aerosols if something were to go wrong? And how do we make aerosol production circular? In other words, reclaim them after they leave the atmosphere so we don't run out of sulfur?
Yeah, so I have to make sure that I'm answering these questions as sort of my understanding of the topic from the reading that I've done and the people that I've talked to. But there's obviously other people that have proposals. There's a variety of proposals and so on. So I think for the most part, what folks are proposing is using materials that are fairly abundant, calcium carbonate, sulfate in whatever form it's manufactured in and put there. And so I think that they're looking at materials that can be put there in these teragram levels. And again, a particle in the stratosphere only lives for a year. It'll fall out into the troposphere and then be precipitated out after that. So we are talking about whatever amount of material is put there that you're going to recharge it every year. I do not know of a way to recapture it. I have not seen anybody propose to, find a way to collect this material. Once it falls out into the troposphere, it sort of becomes part of the particle loading of the lower atmosphere. It finds its way into clouds, it finds its way into droplets and ice crystals, and it comes out of the atmosphere. So I think the answer is they're meant to be abundant materials that you can put there at these levels, and they're not meant to be recovered. They will, as one of the earlier student questions implied, they're going to fall out somewhat unevenly over the surface of the planet.
Mm-hmm. Okay, our next question is from Mark. Is there a danger you could form new clouds over the Arctic during winter, which may impact on the refreeze of sea ice?
Yeah, I think it's a great question. Where are the clouds going to form? And again, I have to kind of go back to how well do the models do at portraying clouds and cloud formation? The answer to that is not very well. I think any modeler that you have talk will admit that. I have seen some proposals with geoengineering that suggest doing this in sort of a tropical area or an area where, you know, the fallout is less likely to sort of impact the polar vortex, this sort of downwelling air over the wintertime pole. But how well that would actually work, how well placement of these particles would work, I think that's a huge unknown. Limited really in our predictive capability right now, our understanding of atmospheric dynamics and so on. So I think you can broadly try to minimize it, but I'm not sure that we would know well enough that you weren't putting particles down through the vortex and potentially having an impact on the Arctic.
Mm-hmm. Well, I find that a little bit scary. Ed is asking, do you think carbon sequestration is scalable? Because you mentioned earlier about how you really do support it and you think it's a good idea.
Yeah, I mean, I think certainly more research is needed in this area. Ed is probably, you know, talking about where are we going to put all of this material? You know, what are the sort of geological formations that we can put them into? I've seen proposals of, you know, essentially freezing it as carbon dioxide dry ice in the Arctic or Antarctic especially. Yeah, is it scalable? I don't know that I know enough about saying where are we going to put all of this carbon. You know, sequestration can also be biomass sequestration, you know, essentially recovering that material through plant-based matter. And, you know, I've seen proposals to sort of cook that down into something akin to a tar or something like that. And then again, you have to bury that material as well. You can't allow it to react and put CO2 back into the atmosphere. So I think there's a number of methods to do it. I don't think that there's any one silver bullet, even with sequestration.
Mm-hmm. Okay. And here's a question by Ronal. What has been the cloud effect of loss of forests and changes in soil carbon? You mentioned earlier about forest fires and, you know, and then there's the loss of forests. So.
Oh, yeah, this is a great question. All right, this is a weird way to answer it. It's a long-winded way of saying we don't know. We have to remember we've only really had highly capable satellites for, you know, decades. Late 1970s, really, that we've had sort of, you know, good global coverage satellite tracks. What did clouds look like in the year 1750, which is this sort of round number used for pre-industrial times? We simply don't know. There are some people that are trying to do sort of cloud proxies, but they're not direct measurements of clouds. There's things like logbooks at lighthouses and from ships about what clouds looked like, you know, going back a few hundred years. But the honest answer is we do not know what clouds in a pre-industrial atmosphere looked like in a global sense. We don't really even know in the year 1950 what they looked like. We certainly, anything before probably the year 1900 or so, we don't even have close to global coverage from even observations. So, you know, what impact have we had? We think we've worked it out, and there are paleoclimate models that try to, you know, sort of project clouds backwards in time. But it's not like CO2 where we can go into an ice core and measure CO2 1,000 years ago. We don't have that knowledge with clouds.
Mm-hmm. Yeah, and that's one of the incredible things that we started changing the atmosphere before we started even studying it, essentially. So, okay, we do have a couple other questions, if that's okay. From Dale, what do you think about marine cloud brightening over the Arctic?
Yeah, very much the same question, Dale, is, or very much the same answer, Dale, as to stratospheric aerosols. If we put a cloud in the troposphere, it is going to change precipitation. And so the water that goes into that cloud and where it comes out is going to be different than if that cloud wasn't there. And so as soon as you change clouds, you're going to make it rain somewhere it didn't before, and you're going to not let it rain somewhere that it did before. And so changes in precipitation for me personally, again, citizen hat on, not scientist hat, for me, those are red lines. I'm not on board with that. If that's the quote unquote solution, I'm not okay with that. Now, would they have a probability of masking temperature rise, especially in the Arctic, where measurements would indicate the highest change in surface temperature? Yeah, clouds would do that, but what else are they doing is sort of the theme of the day, and they're going to change precipitation. Are they going to change atmospheric circulation? Probably. Are they going to change dynamics to some extent? Probably. I don't think you can decouple any of these things from changing clouds.
Yeah, and that's the interrelationship that you're studying. A question from Lisa. Lisa assumes you heard of the ground-based albedo project, here at MEER. And what do you think of the effectiveness of doing albedo manipulation in the stratosphere versus ground-based? Are they comparable in scale of carbon offset?
Oh, yeah, that's a good question. You have to, so just simply in scale. So if we talk about a change on the surface versus a change in the stratosphere, as long as clouds are taken into account, overlying clouds in the case of on the surface or underlying clouds in the case of what you're doing in the stratosphere, then a change in albedo, a reflection of sunlight back is a reflection of sunlight back. So I don't think there's really a fundamental difference between those two, other than at the surface. Again, if this is, I'm sure for this audience, very obvious, but if that photon coming down was reflected back by a cloud, you can't say that you're going to reflect it back on a surface albedo project. And if that cloud is in between and you sort of bounce it, you have to take those things into account. That's just radiative balance. And so so as long as that's done, I think that those two things are solid. I think that a surface modification, which again, we as humans have done this. We've cut down forests, which has changed albedo. We've put crops where crops weren't before. They have a different albedo than the vegetation that was there before. We've built cities where there weren't cities before, things like that. We have some understanding of what that does, what impact that has. Does it change radiative balance above it? Yeah, a little bit. But I don't think it has all of these other side effects of perturbing ozone, not as big of an impact on clouds, not as big of an impact on precipitation and so on.
Okay. All right, good. And we'll just ask one last question. Well, we all, not everybody, but in a lot of areas, we're observing changes in our weather patterns. And so Glenn asked, what is causing, if you happen to know, we know you're not a weatherman, but what is causing the larger than normal hailstone showers? Do you know?
Oh, yeah, that's a great question. Yeah, it's very important to talk about this. So I do climate. Weather is what happens on a daily basis. Climate is what happens on average over years, decades, centuries, and so on. But weather is a part of climate. So I would hope that all climate scientists have some understanding of weather. So hailstones, changes in hail are very poorly understood. So the idea is that you have an initial ice nucleation process, and that forms the nascent hailstone. And then it has to fall through many times a liquid water cloud. And so that hail is kind of like a reverse jawbreaker. It's the ice is falling down and it's picking up some droplets that are liquid and they're freezing onto the surface. And if you cut a hailstone, you'll notice it looks like tree rings, and that's the times it passed through this liquid water cloud and it built up. So changes in hail can be induced by a number of different things. More liquid water in the atmosphere, a warmer atmosphere holds more water vapor and can hold more droplets. An atmosphere with more particulate matter will create more droplets, but those droplets will be on average smaller. And so all of these things can lead to enhancements in hail size. I'm not personally aware of, I don't think it's a global thing where hail has increased in size, but it's another one of these things where I don't know that we really have a record of, what was the average annual hail size going back in time. So I am absolutely sure that in certain locations it has increased. It probably because of those two things that we just mentioned, but I don't know about hail changes in a global sense.
Okay, well, thank you. So we just really are so appreciative that you've come to talk to everybody. We're sorry we did not get to everybody's questions. There were a lot, but we want to thank you, Dan, for coming to MEERTALK today and sharing your research and your knowledge about clouds, ice, and particulate matter. It's so crucial for us to understand these things in terms of climate science and climate change. So thank you.
Thanks for the invite, and moreover, thank you for the fantastic questions, both from the students and the general audience. I really appreciate that. That's the most fun part of these talks.
And to our audience, even if it may not be obvious in your particular geographical location on Earth, we are living in a rather precarious situation. And at MEER, we're trying to help educate the public while working toward a solution. And we invite you to keep learning about Earth's energy imbalance and about climate science, because there is a lot of information out there that can be confusing or misleading. At MEER, we are an almost 100% volunteer staff with only a few paid student researchers at the moment. We encourage you to consider making a donation if you have enjoyed being here. And you can find our YouTube channel, MEER SRM. The donations help to fund materials and sensors for solar reflector field experiments, basic expenses for researchers, and also adaptation equipment that is going to communities that are already adversely affected by thermal heating. And I'll mention just once again that if you do live in the New Hampshire area, we are looking for some volunteers to help set up the MEER array at Plymouth State University and Concord Community College. And lastly, if you heard something, if you learned something from today, please tell somebody else about MEERTALK so they can come perhaps next month. Next month, we will be meeting on Sunday, August 7th, when Michael Diamond will be presenting about the feasibility of marine cloud brightening. So keep August 7th on your radar screen. And thank you, everybody, so much for coming. Good to see you.